Hello chemistry students and welcome to lesson 6.05 where we're going to talk about rate and collision theory. As always, we want to first just mention that there are common core standards that we will be addressing as we go through this lesson. You can certainly pause the video and take a moment to read over these if you would like. You can also locate them in the course by going to course information and then clicking on the standards. Specific to this lab, our objectives, or excuse me, this assignment, our objectives are to explain how various factors affect the rate of a chemical reaction, and we're going to describe the collision theory as a model of reaction rate. Now, we do need to make sure that we have completed the first four sections of Module 6, dealing with thermochemistry, exo and endothermic reactions, calorimetry, enthalpy, entropy, and free energy. If you're still a little unsure about some of those, please go back and review them. You can also watch those videos, attend open tutoring sessions to get some extra help, but be sure you are comfortable with those before you move into 6.05. Alright, so let's start talking about 6.05. When chemists are doing reactions, there are basically two things that we want to consider about that reaction. First, we want to consider how much product we actually get, and secondly, how fast we're going to get that product. In other words, if we are doing a reaction and we're only getting maybe like a 5% yield out of it, going back to module 4, then that's not really a very productive reaction for us. But if we can do a different reaction and end up with 60% yield, getting us the same product, then that would be the one that we would want to do. The other factor there is, of course, the time. If we have a reaction that goes really slow and we hardly get any product over, say a 24-hour period, versus another reaction that gives us a whole lot of product in just a few minutes, then we clearly would want to do the one that gives us the product in a shorter amount of time. So there is a field of chemistry called chemical kinetics that deals with this very topic, studying how fast we get the product and how much of the product we end up with. And this is where the reaction rates come from. Now, when we talk about reaction rates, generally we are talking about the amount of concentration that changes over a given amount of time. All right, so we're starting with a certain amount of reactant. Over time, of course, it's changing, and we're going to look at how fast it is changing from reactant to product, or sometimes even in a reverse reaction, product back to reactant. All right, so to understand where we're getting these measurements for rate, how fast something's changing or how fast the concentration is changing, we need to talk a little bit about collision theory. All right, collision theory simply is the idea that for a reaction to actually occur, the compounds, atoms, or ions need to collide with each other. If the particles never come into contact with each other, then we're not going to have a reaction. Well, not only do they have to collide with each other, but they need to collide successfully. The analogy I like to use is if you have two cars that are going, like 3 miles per hour and they bump into each other, you're not really going to have much of a reaction. You might, get a little bit of paint scraped, but nothing major. However, if you take those same two cars and have them going 50 miles per hour and they run into each other, now we have a really big reaction, right? We got a mess, we got a nice accident, all those type of things. So there are some factors that are important to understand to have a successful collision. And the two factors down here on the bottom of the screen, we have to have sufficient energy and they have to have the correct orientation. Okay, sufficient energy, going back to the automobile analogy I just used a moment ago, basically the cars that are moving faster clearly have more energy, right, because they are moving. So they're going to have enough energy that when they hit, we're actually going to have that collision. We're going to have a reaction, so to speak. With correct orientation, that simply means they're lined up properly. Molecules, of course, have different shapes and structures. If they do not collide in the correct alignment with the proper, positioning, if you will, then we're not going to be able to break bonds and reform the new bonds that we need. So both are critical for a reaction to take place. All right? And of course, when we're talking about successful collision, remember we're talking about making products. Right? That's ultimately what we want to do here. We want to take those reactants, convert them into products. So let's take those two factors and kind of look at them individually here for a little bit. All right, so to look at sufficient energy, we're going to use a Maxwell-Boltzmann distribution curve. And basically, if you look down here on the bottom, this is simply a curve where we have energy on the x-axis, and then we have the number of particles on the y-axis. And you'll notice that we have a small amount of particles with low energy, but the curve quickly goes up, which tells us we have lots of particles in this moderate energy range. And then we start coming back down, and we have fewer and fewer particles with higher energy. So just a side note, if we took the temperature of this particular substance, whatever it might be, its average kinetic energy would be somewhere in this range. And that is, remember what temperature is. It's a measure of the average kinetic energy. So this substance will have, a temperature somewhere around in here. And if we were measuring the temperature. And back in earlier lessons, we talked about how you have to have sufficient energy. Well, this is a graph showing us that not all of those particles are going to have sufficient energy because they're down here in the moderate range. Okay. Now the one on the right has a little more detail added to it. Here they've added in the activation energy. And remember, the activation energy is the energy needed to get the reaction started, or the minimum amount of energy required for a successful collision. Okay, now that we're using collision theory. So in this example, this small section over here in the green are the only particles that are going to have sufficient energy to have a successful collision and react and produce the product we need. The majority of the particles will be over here on this side, and they will not react. Right, so once those particles cross this line, so to speak, and have sufficient energy, then they will be able to react and produce the products. All right, the second one, the orientation, again mentioned a little bit earlier, that this is just simply lining them up correctly. If you look at the example here, I had CH2, CH2 plus HCl, and we end up with CH3, CH2Cl. Now down here, we just had some examples of different ways they can collide. The first one, the white ball there represents the hydrogen. If the hydrogen collides with a double bond between the carbon, we would have a successful collision. The double bond will actually break up and become a single bond. The one hydrogen would then attach to one of the carbons, and then the chlorine would attach to the other carbon. So we break one bond and form two new bonds. Now here you can see in these other three examples are arrangements that would not work. If we had the chlorine colliding with a double bond, that's not going to work. If we have the chlorine colliding outside just with a carbon, that's not going to work. Or even if we have hydrogen colliding with hydrogen. There's lots of different possible combinations, but they're not going to work. The only one that gives us a successful situation is when the hydrogen, the smaller atom, collides with the double bond. So you can see here, just in this illustration, we have 1 out of 4 that are going to be successful collisions for us. So that, again, is going to give us basically a probability of how many successful collisions overall we're going to have. So not only do they have to have enough energy, but the molecules have to be lined up properly for that reaction to occur. Okay, so with that understanding, then let's look at the factors that affect reaction rate. First one will be concentration. All right, so let's say we increase the concentration of the reactants. Well, if you increase the number of reactants, then you have increased the opportunities or the chances for there to be ones with enough energy and the correct orientation. Again, going back to my car illustration, if you are driving your car on a small, rural highway and there's no other cars around, your chances of having a collision are pretty small with another vehicle because you're the only one there. However, if you go drive up and down the thruway, now there are lots of cars around. You have increased the concentration of automobiles. Now you have increased your opportunity to have a collision. That same kind of logic works with the molecules and atoms and ions. When we have a small number of them, we have less of a chance for a successful collision. But when we have more, we're naturally going to have greater opportunities because there's going to be more available. So more will have enough energy and more will be lined up, have the correct orientation. Now, an important note with this one, just because you double the concentration does not automatically mean you double the rate of a reaction. This is a common error that folks make. They think, well, if I went from 1 molar to 2 molar, then that means I'm automatically going to get twice as much product. And that is not necessarily true. There are other factors involved here. So keep in mind that it's not a direct proportional relationship, but it is a direct relationship. You increase concentration, you do increase the reaction rate. All right, the second factor is temperature. Okay, we kind of alluded to this a little bit ago. If you increase the temperature, then you're naturally going to increase the collisions. Okay, now how does that work? Well, remember, again, temperature is the measure of average kinetic energy. And we have to have enough, or we have to have particles with sufficient energy to have a reaction occur. So if we increase temperature, we are going to increase the overall average kinetic energy, which means we're going to have more particles with enough energy to go past the activation energy. Since you're going to have more with sufficient energy, you're naturally going to have more reactions occurring, more collisions. Okay? Going back to our Maxwell-Boltzmann curve here, if we look at that direct relationship here, you increase the temperature, you're going to have more collisions with energy or enough energy to react. All right? So it's a direct relationship. In the curve here, you see we've got the original temperature labeled as T1. That's the blue curve. When we increase the temperature, that's going to cause the average kinetic temperature to move up. Right? So that means we got more energy. Okay, so the average, is roughly here for T1. Now when we increase the temperature, now we're over here for our average. So what happens is we have more particles with higher energy, and you can see that the area under the red line is greater than the area under the blue line. So we end up with more particles having sufficient energy to be involved in reactions. Okay? So again, just a graphical representation of what we're talking about here. You increase temperature, you increase kinetic energy, particles are moving faster, they're going to collide more frequently, and you're also going to have more particles that have enough energy to have a successful collision. So two things when we're talking about temperature. Now sometimes we can't increase temperature or increase concentration. All right. In that case, we would use a catalyst. All right. Well, why would we want a catalyst? Well, let me skip down here to the example real quick. Enzymes, okay, are chemicals that are in our body, and they are used to help speed up reactions. Okay, and an enzyme is an example of a catalyst. Now the reason for that, of course, you all know our bodies have a specific temperature. And if we get too hot or too cold, then things don't work correctly anymore, right? That's why whenever, we're sick, we always check our temperature and see if we have a fever, right? So we have to keep our body at a certain temperature so that everything functions properly. Well, if we start increasing the temperature in our body to make certain reactions happen faster, that's, yes, it's going to help with the reaction, but overall it's not going to help your body because you're going to start, killing cells and things like that. So our next option then is to use a catalyst. And again, for biology, those specific catalysts are called enzymes. Catalysts simply lower the activation energy for us. So if you look at our diagram this time, okay, our activation energy originally was here on the green line, and now by lowering the activation energy, we have more particles that now have sufficient energy, because now we have the green and the orange all together. So more particles with sufficient energy, we're going to have naturally greater amounts of collisions, and therefore more product being produced. Okay, so again, we could increase temperature, we could increase concentration, we can add a catalyst. Now going back to assignment 6.2, I believe it is, with the exo and endothermic, we also want to just mention here how you would see, how you would see a catalyst on a potential energy diagram. Okay, remember in 6.02 we had the reaction pathway and potential energy on the y-axis. And for a normal reaction, we have to increase the energy to get to the activation energy. And then remember, from there, it proceeds on its own to the products. This particular graph that we put up here is an exothermic reaction, just a quick refresher here, because the products have less energy than the reactants. So this amount of energy is the activation energy. Well, when we add a catalyst, again, we lower the activation energy, so now instead of having to go up to the top of the blue hill, so to speak, it just has to go to the red hill. So now with the catalyst, we have a smaller amount of activation energy needed, so we can get the reaction going faster. So two different graphs representing the same thing. Okay, so now we understand the factors affecting reaction rates. You can go back into 6.05, finish up any problems, examples, click on hyperlinks, videos, things like that. If you still need some help, please attend the open tutoring sessions, and you can also use the review sheet found in the Resource Center. For the assignment for 6.05, you'll be doing a virtual lab. With this one, you actually will be writing a lab report, basically explaining two properties that you would test and how you would test them. You do not have to actually perform the experiment. You simply need to have the write-up, which will involve your procedure, the materials used, and what your expected outcomes would be. So when you go into the activity tab, it will give you an outline as to exactly what you need. And again, the three that we talked about were increasing concentration, increasing temperature, and adding a catalyst. So you can use the first two, obviously, would be good ones. And there are some other ones that we've talked about in earlier sections, like agitation, for an example. So there are some different options to that experiment. If you do need assistance with this, we do offer completion sessions. Then check your teacher's announcement page for the schedule, and you can certainly join us for the next completion session. We'll help you out with that assignment. And then when you're finished with your lab report, you will submit it in the assessments section on your class. So I hope this was helpful, and feel free to give us a call, and we'll help you out more if you need it. We'll see you again soon.